My name is Jungsang Kim. I'm a professor of electrical and computer engineering at Duke University and also in physics. Also a co-founder of a quantum computing company called IonQ. Today we're going to talk about what you mean by practical quantum computing. Let's take that journey in it. And here I take a couple of very famous quotes from Richard Feynman, who is a Nobel laureate for discovering a good chunk of quantum physics. He mentioned something like this: I think I can safely say that nobody understands quantum mechanics. And then he also, this is actually pretty important, his view is that paradox is a conflict between reality and your feeling of what the reality ought to be. So in one sense, there is a reality. And then in the other sense, there is our thought or our understanding of the reality. When they collide, the reality is always right, meaning we actually have to then upgrade our model to make sure that we capture that behavior reality into our consciousness, and that is called science. I think a real scientist should always be questioning, what am I missing? Because that's where all new interesting discoveries are made. There are two rules in quantum physics. The two rules is when you throw a baseball, we think about it as like an object that traverses in space, and we think of it as a particle. You can track its position and momentum exactly over time, and that's the Newton way of looking at it. But no, quantum mechanics says, a baseball thrown, or me talking to you here, it's all waves, like these murky waves in the ocean where it propagates and distributed all over the place. If you have a wave, meaning if I drop a stone in a pond, very quiet pond, and then I create these ripples of waves, if I drop two of them, these ripples of waves will propagate, and then they'll actually start to like run into each other, but they will actually pass on. Meaning this wave has nothing to do with that wave, and then they can coexist in this medium at the same time.
Right.
Okay? Now that is the principle of superposition. Superposition means I can have one wave and another wave that can coexist in time. This atom is like a very small unit of matter, and it is formed with a nucleus and an electron going around it. And it turns out that by quantum theory, this electron can actually be in one of many, many states. So let's say we pick two. The electron is in either state 0 or state 1. We're going to name the two states 0 and 1. What this means is this electron, if it's a particle, like a baseball, then it will have to be either in state 0 or in state 1. But if it's a wave, this particle can coexist in 0 and 1 at the same time. And we write it down as a 0 and 1. It can actually coexist with two numbers, A and B. And those are numbers called complex numbers. So it turns out that's the way you have to be. And then, just like the classical laws of physics, we have a differential equation that tells you how this state will evolve over time. Okay? So in that sense, so I mean, this is a differential equation. I mean, it's a complicated equation, but it actually tells you exactly. If you knew A and B at time 0, you know exactly how it's going to evolve over time. So in that sense, it's not that different. But then comes this weird thing called rule number 2. Rule number 2 is if this atom is isolated by itself, that nobody's looking at it and we have no idea what's going on, then this is true. But the minute we try to understand what it is and probe it, then the superposition collapses. Meaning, while this atom, this electron in this atomic state can be in 0 and 1 at the same time and evolve accordingly, when you try to make a measurement observation, you ask the question, are you in 0 or are you in 1? It will actually have to decide. And that decision is really a collapse. All of a sudden, it picks one or the other, and that process is not described by differential equations, and it's like throwing a dice.
So the two rules are completely different.
The two rules are completely different, completely uncorrelated, and there's no reason why. That's just the way it is. It actually does tell you the probability by which you can find a 0 or 1. Okay, there is a probability, and that probability is actually given by these numbers. Okay, so if this is 1 and that's 0, if A is 1 and B is 0, then you're always going to find this in 0, meaning you're going to find this in 0 with a probability of 100%, and the other one is not. But if A and B are exactly the same, then it's really 50-50. Okay, so this time evolution will tell you how it evolves, but when you observe it, it's going to pick one. And the probability of which one it picks is given by this equation. That's the rule of quantum mechanics. All right, so what does that lead to in terms of its superpower? The first superpower is quantum superposition. As I said, the electron in this atom can be in state 0 and in state 1 at the same time. So this means that I can be here and I can be here at the same time if you don't look. It's like magic. Does that make sense?
I just don't understand how number 0 and 1 exist at the same time.
Yeah.
Could you perhaps explain more simply, please?
I can give you some examples, maybe an analogy to help you think about it. Okay, so let me give you an example of this. Let's say I pick a coin, I flip a coin, and the coin is spinning in space. Okay, so while it's spinning, I don't know whether it's going to land in heads or in tails.
Yeah.
So while it's spinning up there, while you have this like uncertainty going on, until I pin it down, I can say the possibility of this guy landing in heads and tails coexist. When the coin is flipping up in the air, it can be in 0 and 1 at the same time, and I don't want to pin it down. Now, but when it lands, when you observe, then it flips, it has to pick one. It cannot be in some ambiguous state by the time it falls onto the ground. It will have to be heads, it has to be tail. That's kind of what it is. So that's the analogy, right? So quantum state is we have a coin flipping in the space, in the air, and only when it lands, when we want to understand what's going on, then it will actually have to pick one. So we're going to allow that ambiguous state or that multiple state being at the same time to be a reality of the universe. This is strange, right? So especially to the deterministic view. Our favorite physicist of the 20th century, Albert Einstein, didn't like this idea. It says God does not play dice. Is that a fact or is that his conviction?
His conviction.
It turned out that was his conviction. He just did not believe that nature should be probabilistic. That's the conflict and paradox. But the reality is that the nature is probabilistic. It does have the randomness built into the universe. And therefore, the universe is not deterministic. And that's good for us. I don't want to live in a world where all of my future is dictated for us.
True.
Right? So it has some philosophical meaning too, but it so turns out that nature is that way. Let's move to the second superpower called quantum entanglement. Okay? We're thinking about two atoms. The electron in this guy can be in 0 and 1 at the same time, and the electron in this one can be also in 0 and 1 at the same time. Now, I can actually think about a superposition state that looks like this. Okay? This is a superposition of both electrons being in 0 and both electrons being in 1. And it's a superposition of that. Mathematically, I can write it down, and because these two states where both electrons are in 0 and both electrons are in 1 are allowed quantum states, I can write down a superposition like this. Okay? Now this has a weird property that makes no sense. Meaning, let's say I have this state that's given to me, and then I can actually push this particle pretty far out, and I only look at this guy. I'm not going to even look at that one. And when I make a measurement, this is going to either collapse to head or tail. Let me make sure that this is a state where the two coins are all flipping at the same time. Okay? But this only has the possibilities of both being in heads and both being in tails. So when I go and look at my first coin and let it drop, and if the first coin landed in heads, the second coin absolutely also lands in heads. But if it lands in tails, the second one also lands in tail. Okay? The observation is, if I prepare this entangled state, I flip the coin, they're all flipping. I don't know which way it's going to land. But what I do know is when one of them lands in heads, the second one lands exactly in the same state. Somehow there's this magic link between these two atoms that when one collapses into 0, then the other one also collapses into 0. Okay, now, that's really strange too. Okay? That's really strange. And sure enough, our favorite Albert Einstein called this spooky action at a distance. So Albert Einstein came up, as we know, with this theory of relativity. And his claim was that information, or you cannot communicate faster than the speed of light, and this seemed to violate it. Meaning I prepared this entangled state, I send one to the moon, second one I have it here. Once I measure it, and if it comes in heads, I know immediately that this thing that is like way, way far out in outer space also collapsed in heads in time scale that's much shorter than the speed of light that can propagate. So that doesn't make any sense, right? And so he called it a paradox. It's called that Einstein, Podolsky, and Rosen, these three people came together and wrote a paper in 1936 It's called the EPR paradox, Einstein, Podolsky, Rosen. Okay? It so turns out that when you dive into the details, this actually does not violate causality, meaning it does not mean that information can actually travel faster than speed of light. But this kind of what's called a non-local correlation, meaning these two things that are connected, and they're not local, because one can be in Earth and the other can be in Mars, and this correlation still exists. That is allowed by the laws of quantum physics. Okay? What this tells you, remember quantum physics has these superpowers that are fundamentally different than classical physics. What this means is that my colleague Bill Phillips, who was a Nobel laureate in 1997, emphasized that the difference between a quantum computer and a classical computer is much more different than a classical computer is from an abacus. His point is both of these use classical representation of information, meaning whether it's an abacus or computer chip, it can only represent one state at a time. Whereas quantum physics, we're using fundamentally different mechanism to actually do computation. So it can never be replaced by a classical computer if it actually works. I give you a little bit of a background of why this is so timely. You all heard about Moore's law. Have you heard about Moore's law?
No, I haven't, to be honest.
Oh, you haven't heard about Moore's law. Okay. Every couple of years, your cell phone or your computers get so much better and faster. Almost like doubling every year.
For sure, yeah.
Yeah. That's called Moore's law. It was actually declared by Gordon Moore, who was the founder of Intel in the 1970s. And he actually observed over the years that every 18 months, your computer gets twice as strong. What does that mean? It means that every 30 years, your computer gets 1 million times better, 1 million times more powerful.
Wow.
What this means that your computers got more powerful and cheaper, more accessible every single year. The computers that we have today, like even a single cell phone, is so much more powerful than the computer that powered humanity's first trip to the moon by a factor of a million, what you carry in your pockets today. And that's only possible because of this Moore's law and the technology trajectory. Now, the interesting thing is this exponential curve, which looks like a straight line here, is really slowing down. Right? You can see that we're starting to hit some limit. Because at some point, the size of a transistor will become the size of a single atom. And I don't think we know how to make computers with a smaller part of an atom. Not only that, this is again Richard Feynman, when you go down to these very, very small devices, your classical world doesn't work anymore. The laws of physics that we used to create these devices don't work anymore. Now we're in the realm of quantum mechanics, not like in the Ant-Man quantum mechanics. Or maybe. I think conceptually, scientifically very different, but conceptually we're going to a very, very different regime where the laws of universe looks very different, where these two superpowers exist. And that means that actually spells the end of Moore's law. And that's, in one sense, very scary. But he had the foresight to see that this is not a risk, but this could be an entirely new opportunity for building new computers that work on different principles. And he speculated that would be much more powerful, although it will be extremely difficult to do that. 60 years down to his first prediction, we're actually building quantum computers today. Okay? So what does this quantum add to machine learning? From all of these studies, although they're simple, we learned a few things. First, we learned that, remember, we're trying to build this model in some mathematical space that captures the structure of the data, right? These features and how these features actually separate A from B. These are all structures that we have in the data. It turns out that when you think about building a large language model that can actually write essays for you, like ChatGPT and all these, that requires a huge model. They typically have models with tunable parameters that are counted in the hundreds of billions of parameters. And you need huge amounts of data to actually train it so that it can actually start to do predictable things. So when you have that much data, you can build an AI model that's pretty accurate. And that's why it took us 50 years since the first AI idea, which was awarded Nobel Prize last year for the Hopfield model in the 60s, to actually build it. We needed huge amounts of data. And the reason that we built it on language is, guess what? We spent the last 30 years digitizing every document we have. Not to build machine learning, but because we wanted libraries to go online. And then we started creating new content directly digitally, right? So now we have this massive amount, like billions and billions of documents of language that are generated and available in digital format. And that's the only reason we can actually train a machine learning model. But there are so many other examples where we don't have that kind of data. Now, it so turns out that what we're observing is you can make this very complicated structure in quantum space much more efficiently, meaning with much fewer parameters. What this means is there is a potential to build quantum machine learning models where you can train and start to like predict reasonably accurate things with a lot less data. This hallucination where ChatGPT will create, if the data is not sufficient, they would actually say things that doesn't make any sense. If you can make more efficient models with less amount of data, you can actually capture the structure more efficiently. Then you can actually start to apply this machine learning and AI to application areas where we don't have that much data. And then I think that can open up new possibilities. Now, I'm not saying we know how to do it yet, but these are the possibilities that quantum computing can open up for you. All right. This is a picture that we took a few years ago, and each of these big boxes are quantum computers. Okay, so these quantum computers are pretty big devices, very similar to the IBM computers you saw in NASA's training center in the movie Hidden Figures. Right? These are big machines. We're kind of in that stage today. Just about 10 years ago, looked like this. It's a research lab, very complicated wiring, lots of things that has to be tweaked. And most importantly, we had lots of people who are sitting in the lab and tweaking this all the time to get this experiment to work. What we have done over the 10 years is to take that and turn it into a system that we can design and manufacture and operate more reliably. And over time, this bench scale system, which is this one in 2018 picture, is kind of the prototype for the quantum computers we have commercially available today. But in some of our research front, we're starting to make them much smaller and much more compact, and much more reliable. Ideally, and then more recent times, people are starting to use some of these chip scale technologies like this to actually start to make them much more compact. So I think there is a progression of technology into the future where a lot of these manufacturing can actually come onto more advanced and integratable technologies to eventually get to a point where we can build quantum computers. And we can also build quantum supercomputers, quantum data centers, where many, many, many of these quantum computers can be connected together to build a much larger system. It's kind of like Moore's law in quantum physics. Remember, Moore's law didn't start until 1970. In the 1960s, we're building computers that kind of look like this, and we didn't know how to do Moore's law. So that technology of the future is yet to be invented. It's for all of us to actually make some effort, be creative, and dive in and create that technology.
Professor, with lectures that we've heard so far, we had math, we had robotics, AI, and now quantum computing. Now, it all feels like it's part of the same, like one shared universe. Would you say that's true?
Absolutely. First of all, there's only one universe, right? And we are trying to first understand it. We're trying to see if we can have a model of a universe we can create, just like the dog and the cat picture, some model in our brains that we can create to understand and predict how the nature will behave. Okay? Some of that is logic, which is what math does. Some of that is structured data, in real-world data, that is not random, but structured data. And that features that we extract is what help us start to build knowledge and models. That's what AI is doing. Robotics is, can we actually now control that into a real-world motion? And can we actually start to affect the real world? Just like we do when we build stuff or when we write on a piece of paper. And quantum is actually the real underlying principles that are different, that only discovered 100 years ago. These are the way that nature works. So science is an act of trying to build a model in our brain so that we can actually understand the nature. Now, when that knowledge becomes very mature, we can actually start to create technologies and use that knowledge to our advantage to actually build more and more powerful tools by which human beings can be more productive. That has been an evolution. And I think in that sense, all of these are different aspects of understanding and affecting the universe around us. Now, of course, the most important question is we can do a lot of good, or we can do a lot of bad. So that decision of how we are going to develop and utilize that technology to the human good is going to be the core question that each one of us have to have in mind as we make the progress in this direction. So we had a great discussion. I'd like to see if you have any other questions you wanted to ask in general, either about or outside the scope of the lecture we just
I do have a question. So when quantum computers become more common, so obviously rich countries can afford more than the poor ones. I want to know about your perspective, whether it would make the world more unfair?
You know, that's a fascinating question. Last summer, I participated in a meeting at UN in Geneva, and they were asking exactly this question, right? A lot of population around the world have access to internet today. It became relatively ubiquitous. Now, of course, in the beginning, people who had internet versus people who didn't, actually there was a discrepancy in that too, but the cost of the technology have become low enough that everybody has internet. What that allows you to do is if we can create a very expensive quantum computer somewhere, but if you can actually continue to reduce the cost of it, you can allow people from anywhere in the world, even if the quantum computer is not in front of you in your room, you will be able to access that. I think over time, it's a question of how we make the cost and the number of devices available to be deployed. And today, you can see cell phones everywhere, right? On the flip side is the question and the challenge that this discrepancy is always, I think there is a huge factor of human innovation that goes into taking advantage of these new tools. For example, if you think about Korea in 1950s, we're very poor. Very low technology levels. But when people dive in, add more energy and innovation into it, you can catch up.
Yeah.
Which means that this advanced productivity, once you get accessible to it, it's really up to the people to innovatively utilize that to try to get ahead. So, of course, making it available to larger population will be an important technological advance. But I also challenge people to be creative. Once you have these tools, it's really up to your innovation and imagination to try to get ahead using these tools. And that can come from anywhere because this is going to increase your productivity by a lot.
I mean, this might be a dumb question, but do you think, have we reached a limit in computing with quantum computing? Or is there even something beyond quantum computing, like in the years to come?
Yeah, you know, that's a fascinating question, right? So we are actually, for quantum computing, I think we're kind of pre-Moore's law, right? So we're still in the very, very early stages. Even some part of it kind of slows down. The actual computational value that we extract out of it continues to improve. Meaning, I don't think we'll come to a point where a computer today, or at any given time, is the same as a computer from 10 years ago. It will always continue to get better in some measure, right? So I think that in that sense, although the number of devices may saturate, I think the actual capability that we utilize will continue to improve. Having said that, for quantum computers, we're still in the very, very early stages. Exactly what that law is going to look like and how long it's going to last, how many decades it's going to last, we just don't know that. So I think it's a little bit too early to say what is the end point of quantum computing slowing down and what the next thing is. It's really for you guys to think about, but I don't think that time will come within my lifetime. So I'm going to focus on what we can do with quantum computing. All right, so we live in a very exciting time where some of the very fundamental understanding of new science to technologies that can actually drive different change lifetime. Now, it used to take a long time, but that cycle is getting shorter and shorter and shorter. So I think we live in a very interesting times where learning new things and understanding new science can actually affect kind of new technologies, and that will affect our lifetimes in a relatively short times. What that means is we need people to actually cross all of these boundaries. The good news is we'll have tools like AI and others for individuals to be so much more productive and start to span across many different regions. I think one of the take-home messages I would love to share with you based on my experience of starting out as a scientist to becoming an entrepreneur and eventually kind of coming back to how we actually think about education on our next generation is the world is changing. And sometimes that's scary because when the world changes, the way that we have become used to may or may not persist. And sometimes we think about how do we adapt to the world that is changing. But an even more important question is the world doesn't change on its own. The world changes because of the things that people do. And the way the future is going to get shaped, it's really up to you and all of us to make of it. So we can actually worry about adapting to a fast-changing world that is unpredictable, or we can actually go and drive that change to the way that we think is valuable. Quantum computing is an example where science has led to a very exciting early part of the industry today, but it is driven by some people who had passion and who was dedicated to making that change happen. It is being shaped into the form that these people actually envision. What I'd like to conclude is the future is not there predetermined for you. And that's the recognition of the 21st century science. What that also means, it's really up to us to create that future, whatever it is. Let's do it right. Because as the impact gets broader more quickly, if we do a lot of damage, it may be very difficult to undo. With that note, I'd like to thank you for your attention and wonderful discussions we had.
Thank you so much.
Thank you.
Do you remember when it's the last time and you actually looked up the skies? I'm Yujin Yang, an astronomer from the KASI, Korea Astronomy and Space Science Institute.
Space.
Astronomers look at something. What?
Maybe alien life.
Trust me, astronomers are very serious about the aliens or Earth 2.0. New Space Telescope PIX. Our knowledge about universe is more colorful. And we just wow mankind's fundamental question, basically where I came from, where I'm going. Secrets of the universe. So let's go on the journey.